All right, so I'm going to look at doing substitution in symbolic algebra. So I'm using what's called a live script. So over here, when you start new, you can do a live script, and it just gives you like prettier answers. You can kind of see some pretty previous stuff I was doing over here. So, well, that's not a really pretty answer, but it's prettier than something else, I guess. So substitution is pretty straightforward. So if I have an equation or an expression, this would actually be an expression, 3x plus 1, and I want to substitute x. Everywhere I see an x, I put a 2. I just run that. Look, f is 3x plus 1, so substituted it's 7. So f answer, I like to have I don't like to have dangling answers around. So it's 7, yay! so that's super fun. Let's say I have some function 3x squared plus 2, well, that's now 3x plus 1, subs fx2, 19, all right. I wonder if I can do this. 2, 3, and 4. Hot potatoes, yes, look, so it's basically substituting in 2, and then it substitutes 3, and then it substitutes 4, so I can get multiple answers. Oh, that's super fun. Let's see, what else can I do? Let's do, I keep using the number 3 because it's my like a middle finger left-hand thing. So z squared plus 7y plus x. All right, so I'm just throwing stuff out there. So the idea is I can throw in, if I want, I can just substitute for x. I'm going to plug in a 2 for x, and what happened to the y? Why? Why did you do that? Oh, because I completely forgot something. There we go. So I can just plug in for a y, and so it still has a z and an x, or a z. Let me try talking again. I can plug into for x, and now it still has a z and a y in it. G answer subs. I can also say, okay, for g, I'm going to substitute in x, y, and z. And I'm going to plug in for that 6, 7, and 8. Oops, go back. Oops. So what you can see it's done is it's put in x for 6, y for 7, and z for 8. And if that's too hard to see, you can plug these in for 0 and 0. So if everything but x is 0, then it should be x. And so that works. I could even take out the x if I wanted. And I could just say, what if y and z are 0? What do I get? And it says, oh, you get x. I'm like, yay. If you really want to be obnoxious, you could put in sets of these, like 1, 2, 3, and then I don't care. Not that I don't care. And then, oops, I forgot to put it in the brackets. So you have brackets inside curly braces, and then you're getting 3 different sets of answers because you're plugging in 3 different sets of stuff. So actually, this could be kind of cool. You can kind of do some interesting stuff with it, but really, that's not my intention here. I'm not trying to get really into the thick of things. I'm just trying to play around and experiment a little bit and just give you some basic functionality of the symbolic, because you can just go nuts in this if you really wanted to. But yay, pretty print. Okay, let's see what else we can talk about. What did I want to do here? Simplify. I wonder what that did. Sometimes I do stuff and then I forget why I did it. Simplify. I can simplify answers. Oh, okay. I understand what I was doing now. Yay. Okay. So you can do all kinds of fun stuff. But now let's also talk about calculus. You can actually do calculus in symbolic matrix or symbolic toolbox, which has probably got some of you thinking, I know how I'm going to get Cal 2 done. The idea is if I have x is equal to something. So here we go. I've got, this is a displacement function. And I can remember that velocity is dx dt. So I can differentiate x with respect to t. And now it's going to give me the velocity. Thank you. And remember acceleration, except I can't spell. Acceleration is the differentiation of velocity with respect to t. But I can also say acceleration too, as I can say that it is the second derivative of x with respect to t. And I should get the same answer both times. Yeah, so I can do a second derivative by either doing the differentiation twice, or I can get a second derivative by just saying do a second derivative. And then from here, of course, you could do the substitution, acceleration 2, where everywhere I see a t, I'm going to put in a 12 seconds. So that would tell me, oh, at 12 seconds, I'm going that fast, which really isn't helpful. So I would have to double the substitution. So that would be my acceleration at t equals 12. So apparently I'm decelerating at t equals 12. But you can play around with that. So differentiation, like it says here, you can differentiate with respect to other variables. It will automatically differentiate with respect to x. So if I say since x, let me do a new section here, so sails are clear. And if I've got y is equal to, can't spell at all, x squared, and I differentiate y, it's automatically going to differentiate with respect to x, even if I have other variables in there. So if I differentiate with respect to x, the t and the z goes away, right? Because there's no x, it's just a constant with respect to x. So if I say nothing, it's going to automatically do it with respect to x. If I do it to another variable, I just have to specify which variable I'm interested in. We can also do integration, which is just as kind of straightforward as you think it would be. Let's see. So if I throw these in here, x squared plus 2x plus 1, and I integrate it, it's not pretty. So integrate y. So that's not how I want to see it either. Let's try expand. There. Okay, so that's a way that I like to see it that makes the most sense. So again, this is just stuff that you play with, and you just kind of decide what you like to see, what you like to look at. For me, looking at this expanded is a lot easier to see. So if I look at these two side by side, I can be like, oh yeah, clearly if y is equal to that, then the integration is this. Now notice it's missing the plus c. So it's automatically assuming, like it doesn't add the plus c part. I wonder what it automatically assumes. Let's go help int. Integrate. It does an indefinite integral, but it just skips the plus c part, I guess, is really what it's saying. But you can integrate on y from 0 to 6. Aw, you don't like that? Oh, no, because you integrate on x. You don't integrate on y. Integrate on x from 0 to 6. You're not happy with me? Oh, I know why you're not happy with me. Let's start fresh right here. I want to integrate on y on x from 0 to 6. There we go. Okay, now it's happy with me again. So I'm going to integrate with respect to x from 0 to 6. If I had something like this again, where I had a t and a z, again, it's going to automatically differentiate or integrate with respect to x. Oh, t and z. So it's going to automatically differentiate with respect to x because it's just going to assume that's what I meant. But I can say, actually, I want you to expand or integrate on z. And see, then the z becomes the 1/2 z. So x squared z, right, plus 1/2 z squared, that part there gets integrated. So you get the same kind of a thing. You kind of get what you would expect by doing that integration. So let's see if there's anything else super exciting to do. No, pretty much just that. You can integrate from the upper to lower limits. And again, really the sky's the limit. There's all kinds of crazy stuff you can do. And again, I'm just going to encourage you to, is it going to let me do that? Or are you going to yell at me? You're not sure if you're going to yell at me. You might yell at me. Let's see what happens. It did kind of get mad at me, but I was able to get it to show some things. There's just like a ton of stuff in the Symbolic Algebra toolbox. You could just do all kinds. This is not actually what I wanted it to be. It's got a lot of the same stuff that all the others do, but you can see the differentiation, the substitution, substitute expressions, collect. So yeah, you've got a lot of fun that you can do with. Got these crazy functions, but there's a lot of fun you can do with the symbolic manipulation. It's one of those things that you're just it's like plotting. Like you don't really know all the ins and outs of plotting until you really have to plot stuff. You'll learn the ins and outs of this if you really need to play around with it. But it's kind of fun, so I hope you enjoyed messing around with this.